Alright, so we're going to be continuing our discussion on thermodynamics here. We're going to be talking about energy and its transfer, and basically introducing some of the concepts needed to understand the first law of thermodynamics. First law of thermodynamics is very important for you guys to use throughout your careers, because it just has so many applications. So I hope, if anything, you take from this class that energy is conserved. You cannot be created or destroyed. So let's take a few examples here where we look at a refrigerator and a fan inside of a system. Now, depending on how we define our boundaries of our system, here the boundaries are the pink line surrounding the refrigerator, the pink line surrounding the fan. Our system will experience a temperature increase or decrease, but work is only crossing through that system boundary, through that outlet. So we have energy transfer to the system, and these are just a few examples of how we may have work either crossing the boundaries, which we've had some examples of that earlier, or we may have something encompassing the system where the work into the room can result in a temperature change within the room. Now, what types of energy are we going to be considering? We're going to be considering, when we talk about the energy in a system, we're going to be first considering only macroscopic. Remember, we're talking about classical thermodynamics here, so we're talking about macroscopic scale. We're going to also consider some microscopic forms of energy. So some of the energies related to the molecular structure, which we're going to encompass in this variable called internal energy. And it's going to, that U will encompass all of the very small amounts of energy associated with the different molecules. Kinetic energy is going to be the energy associated with the velocity of the fluid or the gas or whatever it is that we are dealing with or analyzing, and the potential energy is going to have to deal with the elevation of the fluid or the elevation of the gas or whatever it is that we have relative to some reference point. Mathematically, how are we going to describe these? You may recognize kinetic energy, mass times velocity squared over 2 from some of your physics classes. Potential energy, mass times gravity, and Z here is denoting a elevation change or height. Another thing to notice from this slide is that we have variables listed in all caps and variables listed in lowercase. When we express something in all caps, that denotes that that is taking into account mass. When it is lowercase, it's per unit mass. So the units, when we talk about per unit mass, are kilojoules per kilogram or joules per kilogram. So when we talk about the energy associated with a system, we're talking about summing up all the microscopic energies associated with the molecules in the system. That's taken into account with U. Kinetic energy has to do with the velocity. Potential energy has to do with the change in height. Typically what we'll do is we'll express them in kilojoules per kilogram for most of our problems. So we're going to be dealing a lot with little e here. Sometimes we'll be dealing with big E. A lot of times we're going to be dealing with little e. And although we're going to be first talking about closed systems, if we have an open system, here's a term that's important. We have mass flow rate. Mass flow rate is the density times the cross-sectional area times the average velocity. And we may have to calculate these later on in the course, particularly when we started getting introduced to some fluid mechanics topics. But starting off here, I'll probably give you the mass or the mass flow rate of an object until we get to the point where you need to be able to calculate it, and I will tell you when that point comes. So how are we going to describe this variable U? Well, U is a sum of all of these different types of energies: sensible, latent, chemical, and nuclear. Now, sensible energy basically has to do with the kinetic energy of the molecule. And by kinetic, I'm talking about the movement of the particle, basically. That takes into account translation of the particle, rotation, and vibration. We also have the chemical energy, the bonds between the molecule itself. There's a lot of energy associated with those. And it also takes into account nuclear energy, which is the bonds within the atom nucleus itself. So all of these are encompassed into our internal energy value that we're going to be using in our calculations. So that's the U value here in this equation, and we'll also be adding, when we look at a system, the kinetic and potential energies of that system. Here's an example of an energy transfer device, a turbine. So we have a height difference between two reservoirs. Somebody put a turbine in between these height differences. As the flow goes from a higher elevation to a lower elevation, we can try to capture some of that potential energy using this turbine. And you can look at that. We'll probably work some examples here eventually on how much energy is actually extracted by this turbine. But at least you get an idea of an application of the conservation of energy. Other types of energy that act on our system, so those others, internal energy, kinetic energy, and potential energy, are characteristics of our system. So inside this dashed line. Now we can have things cross our system. We can have heat cross our system, and we can have work cross our system boundary. What's the difference between the two? Well, heat, and we're going to define heat as something that requires a temperature difference between the system and the surroundings in order to exist. So if we have something that is the same temperature, like this soda can, as the room, there's no heat transfer. But if we have something that is different temperature than the surroundings, then we will have heat transfer. Now, the units of heat transfer may be expressed, if we're talking about the rate or per unit time, we'll be talking about watts or kilowatts. Otherwise, we'll be talking about joules or kilojoules. And this can be expressed per unit mass. So here we have kilojoules per kilogram, which may be a common expression for us to use. In the bottom right hand corner, there's a phrase that we haven't really discussed. It's a term called adiabatic. Now, adiabatic, what that means is that there is no heat transfer across our system boundary. Now, we talked about in a couple lectures ago something that's isothermal. Isothermal and adiabatic are not equivalent. Isothermal means there is no temperature change. So the system may be at one temperature and the surroundings may be at another temperature. If they are at different temperatures, we'll have heat transfer. Or if it's not insulated, we'll have heat transfer. That temperature difference can remain constant after we have some process occur, and we would still be having heat transfer from system to surroundings. So even though the process was isothermal, doesn't necessarily mean that heat transfer is not present. So be very careful. Isothermal means no temperature change. Adiabatic means no heat transfer to or from the system. So the next component of energy that we're going to be talking about is work, and we'll be introducing that in our next lecture.